So the focus on this chapter will be ketones and aldehydes. And the biggest thing to remember about ketones and aldehydes is that they're carbonyls. Right? A carbonyl is simply a C double bond up. Right? A carbon has a pi bond and a sigma bond to oxygen. Obviously a very polar bond. And they're found in lots of different things, lots of natural products. Butyraldehyde, vanillin, phenaldehyde, camphor we're familiar with, of course. Carbones. These are cool. The carbones are cool because everything about the carbones are the same except they have this one asymmetric center, right? And based on that, we have these in the lab. We could look at them and smell them. One smells like spearmint. One smells much different, just based on that one stereocenter being different. So these are important functional groups that are found in lots of things, right? Ketones and aldehydes, right? Just to remind ourselves of some of this basic stuff, right? The carbon of the carbonyl group, right, is sp2 hybridized, meaning it has a pi bond, right? It has a p orbital, so it has a pi bond, so it must have a p orbital. Bond angles are 120, of course. The CO pi bond is shorter and stronger than a CC bond, right? So it's a shorter bond. Their resonance forms, right? Think about the resonance forms could be, right? So one resonance form could be where, right, that's shown here, the one that makes the most sense, where in this pi bond, those electrons would go to the oxygen, right? So this resonance form tells us the carbon of the carbonyl group, the aldehyde or ketone, is electrophilic. It's delta plus. The oxygen of the carbonyl group is electron rich. It could be nucleophilic, right? That's what that resonance tells us. What's the other resonance that's not so great is where you take the electrons and give them to the carbon and have the oxygen have a plus charge and not have a full octet, and that's less likely, right? Just based on electronegativity. So the carbon of the carbonyl group is electrophilic. There's your bond angles. There's some ideas about that. Kind of stuff we already know, right? We knew that this carbon of a carbonyl group was an electrophile. Right? So let's talk, and now let's learn some reactions. Let's learn about some reactions. So how do we make ketones and aldehydes? That's what we're going to go through first. So one of the most simple ways is something called ozonolysis. Ozonolysis, which is exactly like it sounds. Use ozone, O3. And the cool thing it does, I always think about like a pair of scissors cutting an alkene in half. And what it does, right, when it cuts it in half, this was carbon 1 and carbon 2, right, as it splits it down the middle, it just puts an oxygen on either side. And that makes two carbonyl groups. So here's an example. So this is carbon 1, carbon 2. There's carbon 1, carbon 2. If we think about splitting this down the middle and putting an oxygen on either side, right, you get two products. So it takes alkenes and kind of splits them. And that'd be carbon 1 and carbon 2. And that's what you end up getting here with O3. And then there's a second step where you add this dimethyl sulfate to get this. I'm not going to ask you to know the mechanism for this, but I am going to ask you to recognize both if you have two ketones or aldehydes, they could come together to form. They could have came from an alkene, right? Ozonolysis can take an alkene and turn it into two ketones or aldehydes. Just be able to recognize that. Other ways that you've already learned how to make ketones and aldehydes. Way back when you were learning about alkynes, you learned about two sets of reagents, mercury and boron, BH3H2O2. And you should remember, of course, both the mechanism and the products of how these work. If you took a terminal alkyne, an alkyne with an H on the end, right, terminal alkyne, if you reacted it with the mercury reagent through a series of steps, you got to an enol, and that turned into a ketone. Anybody remember tautomerization? 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 All right. Who wants? All right, mute, unmute. Tautomerization. Thank you, Todd. Thank you. Yep. Come on. There we go. Ta-ta. That was good. Nice. You guys didn't realize. You knew I was in show choir, right? Singer and a dancer, double threat. Jazz hands. I was in it before it was cool. Yep. people have to turn their mics up. People have to close their cameras because they don't want me to see their faces right now. Very good. So you do a tautomerization to go from an enol to a ketone. Same thing happens with a terminal alkyne, but now a different reagent, BH3H2O2, 2 steps, which of course you know the mechanism for, or you'll look back and figure it out. You get an enol, which again does a tautomerization to get an aldehyde this time. Same starting material, different reagents. One gives a ketone, one gives an aldehyde. Right? So you need to know those. But they both go through that enol intermediate. Enols are a way to turn into ketones or aldehydes. Okay? Should I show what a tautomerization looks like? A tautomerization looks like? I will. So the way I like to think of these, they can be acid or base, catalyzed, or even done in neutral conditions. So let's look at an acid catalyzed version of this. So we're going to get to this, and it's catalyzed, meaning we need to regenerate the H plus before we're done, right? So let's number our atoms. 1, 2, 3, 4. 1, 2, 3, 4. And we're also, of course, making H plus in the end because it's a catalyst. So what changes from the starting material to the product? What new bonds are you forming for the product, and what bonds are you breaking in the starting material? New pi bond, CO pi bond, and you're also adding a hydrogen to carbon 3. Because now all of a sudden carbon 3 has 3 hydrogens, where before it only had 2. So the way this works, the pi bond reacts with the H plus. H plus is the electrophile, right? H plus, strong acid. Make that the electrophile. What's your nucleophile? The pi bond. At the same time, you're going to break this OH bond, and these electrons are going to go there. So what just happened? This H is what became H plus. I'm going to circle that in blue. There it is. There it is now. Right? It lost electrons, became H plus. These 2 electrons between this OH bond became the pi bond between the oxygen and the carbon. This pi bond formed a new bond, a new CH bond, between carbon 3 and that hydrogen. So this is an acid-catalyzed tautomerization. So what if I didn't have acid around? How could I do this? I like to do this kind of probably incorrectly, but it gets me there, and it's just simpler. So again, we're getting to this. So essentially we need to move this hydrogen to this carbon. Carbon 3 as we had it above. 1, 2, 3, 4. 1, 2, 3, 4. Let's just make it intramolecular. Is it probably intramolecular? Probably absolutely not. But because we're a little lazy, we just do it that way. So get to the same product. This is under neutral conditions, right? Neutral meaning there's no acid or base. And here is acidic conditions. If we're doing it in basic conditions, we have a base. So we got our enol again. And we're going to do this tautomerization. Number of carbons, 1, 2, 3, 4. But because we're in basic conditions, the first thing we're going to do is we're actually going to deprotonate. And that's going to create something called an enolate, which you should have heard about at some point. I'm sure you've seen. This is an enolate, whereas this is an enol. These are all enols. Enols are neutral. Enolates have a negative charge. And I said this was base catalyzed, so the last step is going to be we got to regenerate that. So we're going to do a deprotonation, and that gets us back to that ketone through the base catalyzed tautomerization. So one thing we've done, we didn't do a lot of this, but just so you're aware, I'm not asking you to know this right now, but there's ways to add things to benzene rings, which we'll kind of cover later on. When we get closer to the end of the semester, we'll add this in. These are ways to add carbonyls to benzene rings. So be on the lookout for this. It's called Friedel-Crafts acylation, which is similar to Friedel-Crafts alkylation, which you have done in lab before. All right, moving along. So we've done ozonolysis, which kind of scissored up the alkenes. We did tautomerizations when we took a terminal alkyne with mercury or terminal alkyne with a boron reagent. Those are stuff we've learned before. Now we're going to introduce essentially another way to do taking a primary alcohol and turn it into a aldehyde. So it's this DMP, desmartin periodine with an iodine, complements PCC, which we've learned about, as PCC is a way to go from alcohol to aldehyde and not keep going to carboxylic acid, and DMP is essentially doing the same thing. Same rules apply. If it's a primary, you'll make an aldehyde. If it's a secondary, you'll make a ketone. Right? If it's a tertiary and there's no hydrogens on the carbon attached to the oxygen, nothing happens. Right? You need to have hydrogens to remove there. So for DMP, the desmartin periodine, I've gone through that mechanism, so that's in a different video, so make sure you check that out. The DMP, the desmartin periodine, how it actually turns a primary alcohol into a aldehyde. One thing to remember, you may not know, what is OAC? A lot of people want to know what that is. OAC is O-acetate. So OAC is just this. That's what that is. It's a good leaving group because it has resonance like an ester. That's OAC. One last one before we do some clicker questions. You can make aldehydes using this reagent called DIBAL. But they're specific, they react with esters. So DIBAL reacts with esters. It makes this aluminum intermediate complex, and I've covered this mechanism in a different video. And then finally it breaks down, as we've shown before, into an aldehyde. So DIBAL will turn an ester into an aldehyde. So it's another way to make an aldehyde. Right? So you should be learning more and more ways. I can make aldehydes from primary alcohols. I can make aldehydes from alkenes with ozonolysis. I can make aldehydes from a terminal alkyne with BH3 and H2O2, right? Thinking about all the ways you know how to make aldehydes. End of chapter summaries are really good for these kind of things, to take a look and see all the different ways to do it.